Hello everyone. This is just going to be a video demonstrating the visualization for complex addition. Uh, Probably the only visualization I can think of, in fact. Most of you are probably very familiar with this. I'm going to start off with, of course, the Gaussian integers, z of I. And, like I said, most of this will probably be pretty straightforward for most of you people. This is going to be like really simple and straightforward. We're going to pretend again that complex numbers are in fact vectors, or can be represented as vectors, which in most ways they can be, except, well, there are some differences, but I'm not going to go into that in 10 minutes. I'm going to set up a couple vectors representing complex numbers. Okay. And then we're going to calculate a vector sum of these two. Okay. Vector 1 and vector 2 on the Gaussian integer plane. Okay, from that point, we're going to form the parallelogram, which is formed from these two whatever, and their sum, or whatever. You can form from the two sides this parallelogram. You usually do it this other way around. Usually, if you're drawing it, you form the parallelogram actually first. Now we'll just check to make sure that that parallelogram and that vector sum is in fact the sum of these two Gaussian integers in the plane. These 2 points, which represent Gaussian integers on the plane. And of course, 2 plus 4 equals 6, and 5 plus 2 equals 7. Now, for subtraction, what we usually do is we just take the negation of one of them, or the inverse. I think in Cabri here, they consider it to be the symmetric of vector. I'll take it as 2 plus 5i, 2, 5 here. Okay, that's the first thing I'll do to set this up. I will take what they call symmetry. Well, that's the one that works. It'll be the inverse of it. It'll be the negative of this vector, if you will, from this point at the origin. Okay, we'll just make sure that in fact is the one we want. Again, it's coordinates, and indeed, -2, -5 is the negative of 2, 5. And then we'll add that vector to this one, which is the same operation as subtracting. But of course, I mean, if we took this one first, it would make a difference, because of course, subtraction is not commutative. Always have trouble with that word. Okay, we'll take the vector sum, the first one, and the negation of the second one, right from the origin. We'll form its polygon again. Its parallelogram, just so this is very familiar to everyone. Right to there, and then to there, and then to there. Okay, then we'll just take the coordinates of the difference, and indeed we'll see that 4 minus 2 is 2, and 2 minus 5 is -3, or 4 plus -2 is 2, and 2 plus -5 is -3, same operation. Now, I just want to demonstrate, of course, that this does in fact work in other quadratic rings. So, first of all, we'll take z of 2i, or z of I times square root of 2. Okay. We'll set up the axes. We've got to do our calculation. If you don't know how I'm setting up the axes here, I have a couple other videos on that, and you can just refer to those, and they'll explain them, I think, pretty much completely. So, there we go. I want to move this. What are you doing? I don't know what I'm doing here. Undo. Okay. What I wanted to do was to move the axes over here. Yes. I'll move this result down here. Okay. And then we're going to transfer that measurement onto the vertical axis. Boom. And then we're ready to set up our new axes. Boom. Boom. And boom. Then we can just hide the old axes. We can also hide this. I'm going to define a new grid. Alrighty. And this is z of 2i, or z of I times square root of -2, 2i square root of 2. Okay. And so we'll set up a couple vectors, which again, we're pretending are really complex numbers. I mean, I is a bivector. We don't want to go into that now, but some of you will know what I'm saying. Vectors and complex numbers are not, in fact, the same thing. I'm not making that claim for some of you who will get upset about that. But you know, we're just going to pretend they kind of are here. Okay, we're not going to get into that much detail right now. Okay, vector sum of these two. Boom, boom. From the origin again, we're going to form the parallelogram here, and boom, and boom, and boom, and boom. Okay, and then we're just going to take the coordinates to make sure that this is in fact the sum of these 2 points here. Boom. And it would appear that 3 plus 6 is 9 and 5 plus 2 is 7. So that appears to be the sum. Okay, let's take a 1 mod 7. I mean a 1 mod 4, sorry. Right, a 1 mod 4. Let's move this over now. Let's take I times the square root of 7. Okay, or z of negative 7, however you want to put it. Well, the maximal ring of integers of everyone knows what I mean. Okay, I think so. I hope no one's going to be too particular. We need to do a calculation, and divided by 2, and boom, there we go. And we want to transfer that onto the vertical axis. Boom, and then we're going to take a midpoint, right? Boom, boom, and we go back there. Boom, and then we're going to translate. Okay, now we're just going to hide some stuff. Set up our new axes. Hide the old axes, set up the new grid. Boom. Okay, that's z of I times the square root of 7, or the maximal quadratic ring. Yeah, I think everyone knows what I mean. Okay, define our vectors represent our complex numbers. Boom. Alright, then take their vector sum, right? This vector, that vector from the origin. Okay, form the parallelogram. Boom. 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 Back to the origin again. Boom. Then just check the coordinates, make sure that what we have is what we expect. Coordinates at this point. Boom. 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 Okay. And indeed, 9 plus 2 is 11. 2 plus 4 is 6. So it appears to work out. That's fairly straightforward, and you know, it demonstrates that it does in fact work for the other quadratic rings.